This lesson is for FST, lesson 11.2 on the standard normal distribution. The standard normal distribution is a distribution of z-scores, and that is something that we didn't talk about in the previous lesson. Remember that z-scores are a set of data that have a mean of 0 and a standard deviation of 1. We first talked about z-scores back in chapter 3, and when you graph the distribution of z-scores, you get what's called the standard normal curve or the standard normal distribution. So we didn't know yesterday when we did lesson 11.1 that those were z-scores, but now I want you to know that moving forward. When you calculate specific areas under a normal curve, we always refer back to the standard normal distribution. This is done by converting the raw scores into z-scores, as you'll see in lesson 11.3. For now, we're going to examine the connection between probability and the area under the standard normal curve. Consider first the probability that a value in a normally distributed data set is less than the mean. Then the corresponding z-score is going to be less than 0. This is represented by the shaded area in the graph below. So if we're at 0 for the mean and we're trying to find the area below that, obviously that would be 50%. Because the symmetry of the standard normal curve and the fact that the area between the curve and the z-axis is 1, if you look at the whole thing, then the probability that z is less than 0 is going to be 0.5 or 50%. This is what we would expect. So then 1 minus 0.5 is going to be the area above, which is also going to be 0.5. The standard normal distribution is so important to the idea of mathematics that probabilities derived from it have been recorded in tables and pre-programmed into your calculator. We're going to look at the standard normal distribution table next. It gives the area under the standard normal curve and everything to the left of the given positive number A. The number A is how many standard deviations a z-score is above, that's why we're going to the left, above the mean. The table is read in the following way. First, we're going to look at 1.83, and that should generate the number 0.9664. So let's go to 1.83 on the table. And the table looks like this. This is available in your textbook for lesson 11.2. Sorry, I don't have the page number itself. So if we're going to look up 1.83, we go down to 1.8, and then we go over to column 3, and column 3 is actually right here. The first column actually is column 0, so we're going to go over to the fourth column. And so the probability that you'd be less than 1.83 standard deviations above the mean is 0.9664. So if we were looking at it in picture form, if the A value here is 1.83, the area that I'm shading is 0.9664. So let's go back to the notes and try a few more situations. What if you were doing, and this is example 1 out of your textbook, if you were trying to find the probability that z is less than 0.85. So your A value is 0.85, and we'd look that up in the table. So we'd go down to 0.8, and then we'd go across to the 5, and we get 0.8023 there. But what if they ask you something else, like what's the probability that you're at negative or less than negative 0.85? We found that 0.85 and everything to the left of that was the number we got in the table. That was 0.8023. So that's how much space is covered by the graph from that point on and everything to the left. If they ask you for everything less than negative 0.85, now you're below the mean because negative numbers are below 0 and 0 is the mean. So now we'd be trying to find this region. This region here is the complement to the one that we already know. So to find this region, we would just look up 0.85, and then we would do 1 minus that answer, which is 0.1977. So you'll be working a lot with the table in this lesson, and as well as calculating other areas of the table or other areas of the graph, and a lot of the times you'll be using the idea of a complement to do it. The other thing that you'll use a lot is taking away half of the graph. So if you're only looking for a certain portion, but you're given a portion up above, you might take away the half of the graph that you don't need. It's really important, students, that when you're calculating probabilities using the standard normal distribution table, that you sketch it out to get an idea of which probability we're really looking for. I know when I work with students who struggle, as soon as I help them draw the picture and describe what the picture is giving them, all of a sudden the idea dawns on them. So please get in the habit of drawing the picture. That will really help, I promise. So let's look at the next example. You'll have lots of examples like this one. About what percent of the data in a standard normal distribution are within one standard deviation of the mean? One way that it might be listed or worded in symbols is like this, between -1 and 1. So you'll want to draw the picture for that. So if we're between -1 and 1, we're talking about this area here. Now, if you remember back to our information that we learned in 11.1, we already know that the distance between the one standard deviation above and below the mean, we already know that that's going to be 68%. So we wouldn't need the table to help us figure that out. However, what if these numbers here were like -1.2 and +1.2? You'd want to look it up in the table to figure it out. So I want you to do this question again using the information from the table only. So if I look up 1 in the table, I'd be finding this area here. And when I look up 1.00 in the table, I end up with the number 0.8413. Now what I'm going to do with that number is find the complement to it. So I do 1 minus that number and I get this. That's the area above, or the tail that's above the number that I'm looking for. I want to take that tail away from the number that I know. So I do 1 minus, or excuse me, 0.8413 minus the tail, and that gives me the answer that I'm looking for, which is the area in between -1 and 1. So I found the area from 1 and back, and I took away the tail, which is the same as this tail here. So I took away the complement, and I got 68.26, which is actually a more accurate answer than what we had from lesson 11.1 when we said it was just 68. It's actually 68.26. But that's the method you'd want to use to try to find that answer. Another way to do this same question, which has kind of come up through discussions with students, another thing you can do here is use the idea of taking away the half of the graph that you don't want. So let's start this problem again and kind of try it another way. If I know that from here back is 0.8413, but I take away the half that I don't want, I would just be finding this half here, or this portion here. So if I do 0.8413 minus 0.5, that'll give me just the region that I'm looking for. So that's another way to get the exact same answer. Now when I do that, I get 0.3413. Now that's only half of the answer that I'm looking for, so now I have to take that number and double it. So if I double that, I do get the 68.26 again. So that's another way to do it, is take the number that you're working with, get rid of half of the graph, the lower half, and then whatever you're left with, just double that because the graph is symmetric. The last thing I want to look at with students is doing this on the calculator. And students need to be comfortable using both the table and the graphing calculator to handle these questions. Now it says here on the CAS, what I really mean here is on any graphing calculator. You'll want to access the normal CDF command, and the way that you get there is menu, probability, distributions, and you'll see normal CDF. I think it's more near the top, and you want to use CDF because remember we're doing from one number and everything back. So we're doing an addition here. We're doing not just the number itself, but everything prior to it. The calculator will automatically fill in the lower limit for you, usually with either -infinity or that number in scientific notation, which is probably going to be -9e99 or something like that. That number just means negative really small or -infinity. The upper limit is the number that you're looking for, usually that A value. And usually that'll be the only number that you'll need to worry about. The other two numbers are the mu and the standard deviation. Since we're working with standard normal today, we want those numbers to be 0 and 1. There may be instances where we'll type in all four of these numbers, but for the most part in 11.2, we're just going to type in that upper limit. So remember when we did 0.85 earlier? We looked that up in the table by going down to 0.8 and over to 5. We got 0.8023. Let's see if we can get that same answer now using the calculator. So when you do menu probability distributions, you're going to type in normal CDF. The only number that I typed in was the 0.85 for the second number. Hit tab to go over the -infinity symbol, And when you're all done, you hit enter and you get about 0.80238, which is the same thing as what we would have gotten if we looked it up in the table.